So let's talk about slope fields. What are they? So slope fields, if we just, before we even read the description off that's already on the page for us, right, if we break it down, right, field, right, think of like a big field of grass, and slope, right, we know what slope looks like, right? We've been drawing little lines and linear equations and anything like that, finding slopes since, Algebra 1, pre-algebra sort of studies. So a slope field is literally a field full of slopes. So if you're thinking about like a soccer field or something, you want to think that every blade of grass is representing the slope of a tangent line to a specific differential equation. So to be a little bit more specific, slope fields are what we would refer to as a visual representation of a differential equation. So they show you the slope at every given point. So when you're looking at them, you can actually start seeing solution curves. What are the equations that would have that differential equation with it? These are also sometimes called vector fields since vectors give direction and magnitude and angles and stuff. So slopes are often referred to as vector fields. A slope field shows what's happening at each xy point for a differential equation. So aka that shows the small piece of the tangent line to that point for any solution curve that passes through that point. So in other words, when you create a slope field, you're drawing tiny little tangent lines at all of the coordinate pairs on the graph. And that's just showing you what the equation is doing at each point. So it's just giving you the slope and showing you how the equation is changing there. So for example, I have a slope field down at the bottom of the page, and that's the slope field for the differential equation dy dx equals x squared minus y. So we can't solve that differential equation. X and y are not separable here. So we can't algebraically, integrally, right, using integration, we can't solve for the solution curve, but we can look at the slope field and get a lot of information about the solution curves from looking at the slope field. So like I just said, slope fields can tell us a lot of information even when we don't know how to solve that differential equation, just like the last one where it's not separable. There are other differential equation techniques to use for non-separable equations, but we don't cover them in AP Calculus. So if we can't solve the differential equation, or even if we can, sometimes it's really helpful to look at a slope field just to get a lot of visual information and to kind of see what all of the solution curves are going to be looking like. Because we can draw a variety of solution curves for a large number of initial conditions and kind of see what's changing as our initial condition changes on the field. So one thing to take note of for this is that when you're drawing a solution curve on a differential equation like slope field, right, those solution curves are called unique if no two curves in the slope field intersect. So basically you want to be looking to see if you're basically just doing vertical translations of your curves. If not, we don't call them unique solutions. So we're going to do a couple of examples here. So we're going to draw the particular solution, and this is the same differential equation slope field as the previous page, given that 2, 1 is on the curve. So 2, 1, I'm going to first graph my initial condition. I'm just going to zoom in on the slope field here. So then you're just kind of following the tangent lines as you go in and out of the point. So I'm going to go to the left first and follow the slope. So if I'm going out to the left, I'm going in this direction, and as I'm heading here, my slopes are getting less steep. And as I angle, it's getting probably like there. And it looks like I'm going over here and hitting a vertical at some point. Okay, and then if I follow it out to the right, now going in this direction, back that up a little bit. We're going straight out, and it looks like we're just kind of going out here. Right. So we could do a variety of different initial conditions. So that was if I had 2, 1 as my initial condition. Right, but you're just kind of following the slope field. So I'm going to do one more, for instance. I'm going to do the point, I don't know, we'll do 0, 2. So if I go out to the left now, I'm following the point up. And it looks like I'm kind of going up, 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 up. Actually, I don't like that curve, so we're actually heading up, kind of like that. There we go. And now here, if I follow this out, I'm going out towards this. I'm kind of hitting that horizontal section, and then it's going up like this from here. So that kind of tells me it's kind of forming a parabola shape there. It's probably not quite parabolic, but pretty close to it, right? Visually, it looks like a parabola. Right, so just by changing those initial conditions, right, we have very different looking solution curves. So I actually went ahead and found the solution to that differential equation. So remember, that was dy dx equals x squared minus y. And I actually graphed 3 different solution curves. So the green curve is the 2, 1 curve that we started with. I drew it in blue on the previous graph. I actually graphed it in the same color, orange, on the previous graph for 0, 2. But if we take this new one now at 2, negative 4, sorry, dyslexic moment, negative 2, 4, right, this point up here, now it looks cubic. So we can kind of see that even though this is one slope field for one differential equation, if we move that initial condition around, our solution curves can look very different from each other, right? The orange curve looks like a parabola. The green curve is almost linear. It's probably also a cubic function because it's got a little bit of curve to it. And then the red one is like almost that like characteristic cubic function, what we typically see, right? So wherever we're moving the initial condition, our solution curves might look vastly different. Okay, so we're going to practice creating our own slope fields and using them to draw particular solutions. And I just realized I didn't change the number here. There we go. Okay, so we're going to sketch the slope field for y prime equals x plus y. And we're going to focus on that before we even think about the rest of the directions. So you want to just think about it in terms of the points. I'm going to make my pen size a little smaller. So, right, like I have the point 0, 0, right? So if I plug in 0, 0, I'm trying to think about where to show my work. I'll just do it here. Right, if I use the point 0, 0, y prime is equal to 0. So I'm going to draw a horizontal tangent piece there because that would be a slope of 0. Okay, now if I do the point 1, 0, right, y prime equals 1 plus 0, so that's just equal to 1. So when I go to graph that piece, I'll graph it in blue, right, slope of 1, you just want to do your best to draw a slope of 1. So if you're taking the AP exam, they're really looking for you to accurately be able to draw slopes of 0, 1, negative 1, and then everything after that is just relative. So if you have a higher slope, a steeper slope, they just want to see that you draw steeper lines. If you have a less steep slope, like a slope of 1/2, they want to see you draw a less steep slope line. But they're looking to see that you can actually graph those like y equaling 1, negative 1's slopes like that. Okay. So now if I go to the point 1, 0, right, that's going to be 0 plus 1, so y prime is going to be equal to 1 again. Right, and then we're just going to keep going like that. Okay, so maybe I go out to the point 2, 0. That's going to be 2 plus y. Okay, so that's going to be 2. So that's just going to be steeper, right? And then as I go out, that's just going to keep getting steeper there, right? Because it's 3. So then if I go up a row, I'm actually going to finish doing let's just do the x-axis, the y-axis. I meant the y-axis. So if I go up to 0, 2, I get the same thing, slope of 2. So just want to make sure it is steeper than that. Sometimes I kind of like imagine with my pencil that I'm going to connect the dots for the correct slope, and then I just make a shorter line. Okay. If I go down the y-axis now to 0, negative 1, I get a slope of negative 1. And then 0, negative 2, I get a slope of negative 2. Okay, and then we're just going to keep going. I'm just going to start drawing some lines. Okay, so I got the point 1, 1, so I'm going to get a slope of 2. Okay, at 1, 2, I'm going to get a slope of 3, so even steeper. Do our best. Okay, we've got, 2, 1, slope of 3. I'm actually going to go through and I'm going to make those red. Like Apple Pencil work. Right, and I'm only doing that so that way we can kind of see what all of those same slopes are. I like to color code. You don't have to. Okay, I'm I'm not going to do all of these points because that would be ridiculous. Okay, if I do the point 1, -1, I'm going to get a slope of 0 here, right? So we can kind of see that they're happening on diagonals, right? -1, 1, I'm going to get a 0. -2, 2, I'm going to get a 0, right? So we have this diagonal line situation happening. So once you kind of recognize some of those patterns too, and that they're always going to work out, that kind of makes drawing the slope fields a lot easier, right? So if I have -1, 2, I'm going to get a slope of 1. If I get 2, -1, I'm going to get a slope of 1. Slope of 1. Okay. So I'm going to get my -1 slopes here. And then, right, if I have 1, -2, that's also going to be -1. Sorry for the awkward pause. Okay, if I do -1, -1, that's going to be a -2. Right, so we're going up like this. So we can kind of start seeing what's happening here. I don't know if I'm going to go out much further than this. Okay, if we got 2, 2, that's going to give me a slope of 4. I don't know. Haven't used lime green yet, so it's pretty vertical. So that's also going to be pretty vertical. And what about over here? If we go out -2, -1, that's a slope of -3. It's going to go like that, right? And then they're just going to get more negative from there. We're not going to finish the rest of it. Let's go on to the second part of the question. So if we want to do this at, I'm going to use my highlighter tool to do this. So we're going to draw the graph that goes through each of these initial conditions, the point 0, 1. So maybe using a highlighter is not the best thing. We're going to do it anyway. We're rebels. No, we're not. Okay, just make a fatter line. Okay, so we've got 0, 1, so I'm just following the curves out of it. So I'm following this out, and then as I get over here, I'm kind of zeroing it out, and then I'm kind of hitting this line here. I'm actually going to end up being asymptotic to that. So I'm going to ride that all the way up because all of those slopes are the same. So once I hit that, I'm always going to have that slope. And so now as I come out over here, I'm moving over and getting steeper as I go up. So we're going to go up like that. It's a little awkward looking, but you just do the best that you can when you have to draw these particular solutions. Okay, if I want to graph at -1/2, -1/2, right? So that's not a unit point, right? It's not whole numbers, but we can still graph it. So I got to -1/2 and then -1/2. So I'm like here. And then we're just kind of graphing where we're at. So if I come out to the top, right, I'm kind of really steeply approaching these and then going off asymptotically. And then here as I come out, I'm getting more and more steep here. So I'm kind of curving like this. And this just takes practice. You're just kind of following the little baby steps, like all those little tangent points. And if you're having trouble graphing it because the spaces are too far apart, you can graph tangent line slopes. Like you can graph all these slope lines at like the half points too, just to give yourself more data. And then the last one I'm going to do is 1, 0. Actually, I'm going to make that a -1, 0 because I want to show you that, and that was a typo. Okay, so -1, 0. So I can see how I'm on this line where all the slopes are 1. So as I follow it out, I'm still approaching slopes that are 1. So I'm actually going to ride this straight line all the way down because all of the solution curves are pointing at other points that have the same slope. So they're just going to continue to ride through each other the whole time. So it's kind of an interesting scenario. Okay, let's do number 2, and hopefully it won't take us as long, and there it shouldn't because there's way less points. Okay, so we're going to sketch the slope field for y equals x squared plus y squared minus 1, and then we're going to draw the graph that passes through the origin. Okay, easy enough. So, right, let's start with the origin then. So if I start at 0, 0, y prime is going to be -1. Okay, and then if I go to 1, 0, I'm going to get y prime is 1 plus 0 minus 1, so we get a 0 there. Right, if you want to do all this in your head, you totally can. Okay, if I want to go to 1, 1, that's 1 plus 1 minus 1, so that's going to give me a positive 1. Right, and then I'm just going to keep going with my work here. I'm just going to start doing it in my head now. So at the point negative 1, 1, I should have a slope of 1. At negative 1, negative 1, that's 1 plus 1 minus 1, so I should also have a slope of 1. And at 1, negative 1, also going to have a slope of 1. Okay, so then I want to draw the solution curve for the point that goes through the origin. Okay, so I'm going to graph the origin from my initial condition, and I follow it out the tangent line. And then kind of getting out over here. So then as I come out to the right, following the tangent line, I'm getting closer to the 0 point, so kind of zeroing it out, and then I get close to that slope of 1, so I'm going out like this. Okay, so last one, we're going to do our own again, and so if you are ready to practice on your own, go ahead and pause the video, try this on your own, and then see if your solution matches mine. So I'm going to draw that slope field, and then we're going to graph the solution curve that passes through 1, 1. Okay. Negative 1/2. Okay. Okay, so when I'm drawing my solution curve here, right, I went out kind of through that slope of 3. I'm getting less slope as I go, less steep as I go down. And then I hit that vertical asymptote where it's undefined slopes, and I'm actually just going to stop my curve when I hit that. Because we don't know what's happening there, so we can't make that jump to the other side of the graph. And then we're just going kind of out and steeper as we go up. So we can only draw that section of the solution curve because of that undefined slope section. So whenever you hit an asymptote like that, like an undefined section, oh my god, software updates, you just have to stop. You